Okay, this is section 13.4, and this is Green's theorem. And Green's theorem is basically one possible shortcut to a line integral. So when we think about line integrals, we could use techniques from 13.2 where we convert all the variables to x, or convert all the variables to y, or possibly convert all the variables to t in order to analyze and evaluate the line integral. We also, if the particular vector is conservative, we also could use the fundamental theorem for line integrals. However, in both these cases, it might be just too difficult, or if f is not conservative, it's going to be impossible to use the fundamental theorem of line integrals. And so when we have an integral that's in this written form, this line integral, excuse me, that's in this written form, um, it may be a situation where we want to utilize Green's theorem. And Green's theorem is a very interesting theorem where you actually take this line integral that we have here, this single line integral, and we convert it to a double integral, and we can evaluate it more easily, believe it or not, with a double integral than we can with a single line integral. The issue is that you need a curve that is closed. So you need a curve as it's drawn here in these couple diagrams in your notes. We need a curve that is going to start and end at the same point, and that it traverses through that one time. So Green's theorem is a possibility in a situation like this. The orientation is really important, however. So when you're looking at a positive orientation, that means that you're traveling around a closed curve counterclockwise, and that's positive orientation, and negative orientation would be traveling around clockwise. Now, if you happen to have a situation where you have negative orientation, not a big deal. You can just evaluate it and then multiply by -1. And we talked about those properties in 13.2. But if your path is opposite the one that you're being told to calculate, you can just simply multiply by -1. So just keep that in mind in terms of the orientation. And you can read through in our notes Green's theorem. I won't prove it for you. It's a very complex proof, really time consuming. But here is Green's theorem. And again, it's quite remarkable. We take a single integral, single line integral, and we convert it to a double integral. Now, if you look, and if you remember from what we had talked about in the last section, your vector f is going to be made up of p and q. Now, if you remember, if it's conservative, the derivative of p with respect to y is equal to the derivative of q with respect to x. In this case, remember what I said is that we really can't use Green's theorem if the vector is conservative, and we really wouldn't want to anyway, because if the vector is conservative, we could use the fundamental theorem, and it's way faster. But Green's theorem, if you notice, this inside this integrand, if the vector is conservative, then the inside of this would be 0, which again would be a bit of an issue because that wouldn't help us much. So if you have a conservative field, do not use Green's theorem. If you don't have a conservative field, vector field, and if it is closed on a positive orientated curve, then you can use Green's theorem. And Green's theorem is simply just the derivative of q with respect to x minus the derivative of p with respect to y. And the slight adjustment here is that now it's a double integral over the region. So the region that we're analyzing that is closed to the curve itself, that region D is what the double integral is over. So we're double integral over the region D, and the integrand is going to be this formula here, and then this is going to either be the dx dy or possibly dy dx, or you can imagine it could turn into a polar situation depending on the situation. One last thing is that when we're dealing with a situation where maybe Green's theorem applies, we may see an alternative notation, and it's a line integral, and all this means here is that we're on a closed, positively oriented curve, and so you might see a little circle kind of in the middle of the integral symbol, and that's just another way of writing this type of line integral. Okay, the next video we'll start going through our examples in the notes.